My. We are definitely getting down to it. This is lesson 32 in Math 221 Calculus 1 at SUNY Geneseo. This lesson deals with the net change theorem. And the net change theorem reads as follows. The new value of a changing quantity equals the initial value plus the integral of the rate of change. So if I want to know what a particular function is at some point, and I know what the function is at some other point, then the integral between those two values of the derivative gets me what I want, gets me the new value of a quantity that is changing. The way that this is best understood for me is this. If we take the integral from a to b of some derivative, we take an antiderivative of this f prime, evaluate at b, evaluate at a. So this screencast gives us another way to take a look at what the definite integral does. So, example 1. So we'll just pretend that we have some particle and it's moving on a number line, and its velocity is given by t squared minus 2t meters per second on the time interval from 0 to 4. And we want to know what is the net displacement of the particle. So displacement, we should talk about the difference between distance and displacement. Displacement just means the difference between your starting position and your ending position. So the football runner who runs left, runs right, runs left, runs right, runs left, runs right, and then falls forward for a yard has run a great distance, but has only a displacement of 1 yard. This is the difference between distance and displacement. If we want the net displacement, then we calculate the integral from 0 to 4 of velocity. Why? What does that do for us? It gives us the position at 4 minus the position at 0. Why? Because position is the antiderivative of velocity. So we take the antiderivative, sub in 4, sub in 0, and subtract. So in this case, we are integrating t squared minus 2t dt. Well, how do we do that? We take an antiderivative, plug in 4, plug in 0, and subtract. What is the antiderivative of this polynomial? Well, we add 1 to the power and divide by the power. We add 1 to the power and divide by the power. Sub in 4, sub in 0, and subtract. Sub in 4, sub in 0, and subtract. So if you're good with arithmetic, this turns out to be 16/3 meters. What does this mean? This means that the particle is 16/3 meters farther along in the positive direction when time equals 4 than at time equals 0. That's what that means. Doesn't matter, the particle can go backwards, forwards, doesn't matter. The difference between its starting point and its ending point, at its ending point, it's 16/3 meters further along in a positive direction. How do we know that the particle moved backwards and forwards? Well, the velocity graph looks like this. From time equals 0 to time equals 2, the velocity is negative, which means the velocity is negative, which means that between time equals 0 and time equals 2, the particle is moving backward. And then after time equals 2, the particle is moving forward, which helps us ask the follow-up question, 1b, what is the total distance traveled on 0 to 4? Well, that requires knowing what the integral from 0 to 2 is and knowing what the integral from 2 to 4 is. Because this is the going backward part, and this is the going forward part. They both get figured out exactly the same way. This is 1/3 t cubed minus t squared evaluated between 0 and 2. This is 1/3 t cubed minus t squared evaluated between 2 and 4. Take a moment, sub in 2, sub in 0 and subtract, sub in 4, sub in 2 and subtract. Okay, I'm going to assume you paused the video to do that. This one turns out to be negative 4/3, and this one turns out to be 20/3. So let's think about what's happening. The going backward part set the particle back 4/3 in a negative direction. The going forward part moved the particle up 20/3 in a positive direction. So the total distance is the absolute value of the negative 4/3 plus the absolute value of the 20/3, and that's 24/3 or 8 meters. That is the total distance traveled. So the displacement was 5 1/3 meters, but the distance was 8 meters. Okay? Okay. Let's take a look at one other example. So this is the power usage in hundreds of watts per hour. So imagine it's some town like Springfield, and they use power. Springfield uses power. So there's a rate at which they use power, and that rate is given by P of t equals 11.5 minus 7.5 sine of pi t over 12. And that's in hundreds of watts per hour. So the question is, how many watts of power does Springfield use in a day? So this is a rate, but this is an amount. So when we want to convert from a rate to an amount, that involves an integration. We've got to remove a factor of time, and integrating with respect to time removes that factor of time. So if we were to integrate P of t we would find the amount, the number of watts that are used by Springfield over some interval of time. We're supposed to find out what the usage is in a day, so that's 24 hours. So then how does this go? Well, we take some antiderivative, plug in 24, plug in 0, and subtract. Antiderivative here is pretty straightforward. Antiderivative here is a little bit tricky. I have to ask you to trust me on this one because we haven't talked about the thing that needs to be done to do this. So I'm just going to ask you to trust me on this. You can check yourself. You can take the derivative of this with the chain rule. You're going to get a negative sine of this angle times the derivative of this angle. That's pi over 12. And that pi over 12 is going to cancel out with this thing and leave you with 7.5. So we sub in 24. Sub in 24. Oh. Then we sub in 0 and subtract. Well, the cosine of 2 pi is the cosine of 0, so these are the same. That is 0. So 11.5 times 24 is 276. 276 is the number of hundreds of watts. So this means 27,600 watts in a day. The moral of the story here, we had a rate of change. We wanted to talk about an amount by which we changed. To go from the rate of change to the amount of change involved removing a factor of time, and that was done by integration. So that's a key. I'm going to make a supplemental video, and it's going to talk through a final exam question from a couple of years ago that I think will be helpful to you. Okay, thanks.